Look up at the night sky. What do you see? A scattering of stars, the faint glow of distant galaxies, and the endless black expanse between them. But that darkness isn't empty. It's filled with a cosmic tapestry so vast and mysterious, it defies comprehension. Welcome to the interstellar medium, the hidden fabric of space itself, where dust, gas, and energy swirl in a dance older than time. This isn't just emptiness, it's a frontier teeming with secrets waiting to be uncovered. And today, we're diving deep into 25 of its most baffling enigmas, each one a puzzle that could rewrite our understanding of the universe. Think about this for a moment. Every star, every planet, every speck of light you've ever seen exists within this invisible ocean. The interstellar medium is the cradle of creation, the raw material from which solar systems are born, and yet we've barely scratched the surface of what it holds. Somewhere in that cosmic fog, particles move in ways physics can't yet explain. Magnetic fields twist into impossible shapes, molecules form that shouldn't exist. And perhaps, just perhaps, clues to life itself are hiding in the void. What makes these mysteries so thrilling isn't just their scale, it's the fact that each one pulls us closer to answering the biggest questions of all. How did everything we know come to be? Are we alone in the universe? And what else is out there, lurking in the shadows between the stars? Over the course of this journey, we'll uncover strange anomalies, encounter cosmic ghosts, and even question whether the laws of nature work the same way in the depths of space. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The interstellar medium isn't just a backdrop, it's a story. And we're just starting to read its pages. Picture this, an invisible force shaping the cosmos, bending light and holding galaxies together, yet we can't see it, touch it, or even detect it directly. This is the enigma of dark matter, the ghostly substance that makes up roughly 27% of the universe and permeates every corner of the interstellar medium. We know it's there because of its gravitational grip. Stars orbit their galaxies too fast for visible matter alone to hold them, and entire clusters of galaxies move as if tugged by something unseen. But what is it? That's where the mystery deepens. For decades, scientists have chased clues like cosmic detectives. Some theories suggest dark matter could be made of exotic particles, WIMP, or weakly interacting massive particles that barely interact with normal matter except through gravity. Others propose actions, ultra-light particles born in the early universe. Then there's the wild card idea. What if dark matter isn't particles at all, but primordial black holes forged in the chaos of the Big Bang? The problem, after countless experiments, underground labs, particle colliders, even telescopes scanning for gamma-ray flashes, dark matter remains stubbornly invisible. Here's what makes this so thrilling. Dark matter isn't just hiding in the void between stars. It's the scaffolding of the cosmos, the hidden architecture shaping everything we see. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. Yet its very nature defies the rules of physics we've built our understanding upon. Somewhere in the interstellar medium, between the dust and the starlight, the answer might be waiting, a clue that could rewrite the textbooks. Until then, dark matter remains the universe's most elusive shadow, taunting us with its silence. Now, let's tackle another cosmic riddle, one that hits closer to home. Scientists have meticulously mapped the universe's matter, but something doesn't add up. According to our best calculations, about half of the ordinary matter, the stuff that makes up stars, planets, and even us, has simply vanished. This is the missing baryon problem, and it's forcing us to rethink what we know about the interstellar medium. Where did these baryons go? They're not hiding as dark matter, those are separate mysteries. No, these are the protons and neutrons that should be floating between galaxies, detectable by their faint glow. Yet when we tally up all the visible stars, gas, and dust, nearly 50% of the expected matter is unaccounted for. It's like balancing a cosmic checkbook and realizing trillions of dollars have slipped through the cracks. Cutting-edge telescopes might finally be uncovering clues. Some researchers suspect these missing baryons are lurking in vast, diffuse webs of hot gas filaments so faint they've evaded detection until now. Imagine a spider's silk thread stretched across a football field, nearly invisible unless you know where to look. That's the challenge, spotting these whisper-thin strands of million-degree plasma woven between galaxies. Instruments like the Hubble Space Telescope and the European Space Agency's XMM Newton are now catching faint X-ray whispers from these structures, hinting at where the universe stashed its missing matter. But there's another twist. Some baryons may have been flung far beyond galaxies by violent cosmic events. Supernova explosions and black hole jets could have ejected them into intergalactic space, scattering them so thinly that they blend into the background noise of the cosmos. It's like trying to find a single lit match in a stadium floodlight. Solving this mystery isn't just about accounting for lost particles. Those missing baryons hold clues to how galaxies form, how cosmic structures evolve, and even how elements essential for life, like carbon and oxygen, get distributed across the universe. Every atom we can't explain is a thread in the larger tapestry we're still learning to read. The interstellar medium isn't just empty space, it's a dynamic, ever-changing ledger, and we're only beginning to decipher its entries. Streaking across the universe at nearly the speed of light, cosmic rays are some of the most energetic particles in existence. And yet, we still don't fully understand where they come from. These aren't rays in the traditional sense, but atomic fragments, protons, electrons, even entire atomic nuclei hurtling through space with enough force to rival a major league fastball. They've been detected with energy so staggering, a single particle carries the punch of a falling brick. But here's the puzzle. The sources capable of accelerating particles to such extremes remain elusive, hidden somewhere in the tangled web of the interstellar medium. One leading suspect, supernova remnants, the violent aftermath of exploded stars. When a massive star dies, it unleashes shockwaves powerful enough to sling particles across space like a cosmic pinball machine. These shockwaves could theoretically accelerate cosmic rays, but there's a catch. The highest energy cosmic rays we've detected pack millions of times more energy than even supernova can explain. That discrepancy has sent scientists scrambling for answers, probing everything from colliding galaxies to supermassive black holes. Then there's the detective work of tracing these rays back to their origins, a task akin to finding the source of a bullet by studying the hole it left. Cosmic rays don't travel in straight lines. Their charged paths twist and spiral as they weave through interstellar magnetic fields, erasing clues about their birthplace. To complicate matters, by the time these particles reach Earth, they've often been scrambled beyond recognition, shattered into secondary particles by collisions with our atmosphere. It's like trying to reconstruct a shattered vase from the fragments alone. Yet, the hunt isn't hopeless. Innovative observatories like the Pierre Auger Observatory in Argentina and the Ice Cube Neutrino Observatory in Antarctica are decoding the secrets of cosmic rays by studying the showers of particles they create when they strike the atmosphere. And there's tantalizing evidence linking some ultra-high-energy cosmic rays to active galactic nuclei, monster black holes spewing jets of plasma into the void. These cosmic accelerators could be the engines behind the universe's most energetic particles, but confirming that requires catching these rays in the act, a feat that's like spotting a single firefly in a thunderstorm. Why does this mystery matter? Cosmic rays aren't just space curiosities, they're threads woven into the fabric of our universe's history. They influence star formation, shape the chemistry of interstellar clouds, and may even play a role in the mutations that drive evolution on Earth. Unlocking their origins wouldn't just solve a cosmic whodunit, it would reveal the invisible forces shaping the galaxy around us. Every high-energy particle crashing into our atmosphere is a messenger from the depths of space, carrying a story we're only beginning to decode. Stretching across the sky like the remnants of a celestial explosion, enormous loops of radio waves pulse silently through our galaxy, structures so vast they dwarf entire star systems. These are the Great Galactic Radio Loops, and they're among the most baffling features of the interstellar medium. First discovered in the 1950s, these loops emit intense, non-thermal radio signals, suggesting they're charged with high-energy electrons spiraling through magnetic fields. But what could create such colossal, perfectly curved formations? The answer remains as elusive as the loops themselves. One of the most prominent, Loop 1, spans over 100 degrees across the sky, so large, if it were visible to the naked eye, it would appear 20 times wider than the full moon. At first glance, these loops resemble the aftermath of supernova explosions, the kind of shock waves you'd expect from dying stars. But here's the catch: their energy signatures don't match. Supernova remnants typically emit X-rays and gamma rays as they cool, while these loops glow predominantly in radio wavelengths, their energy curiously focused. Even stranger, their symmetry defies the chaotic aftermath of stellar explosions. It's like finding a series of perfect smoke rings in a battlefield. Nature rarely creates such precise shapes by accident. Theories abound, each more tantalizing than the last. Some astrophysicists propose these loops are relics of ancient starquakes, massive seismic events on neutron stars that sent shockwaves rippling through the interstellar medium. Others suggest they're the fingerprints of past galactic center outbursts, where our supermassive black hole, Sagittarius A star, violently ejected energy in bipolar jets millions of years ago. Then there's the more exotic possibility. Could these loops be evidence of dark matter annihilation, with invisible particles colliding and releasing bursts of radiation that sculpt the gas around them? Yet none of these explanations fully account for the loop's scale, structure, or longevity. They persist for millions of years, outliving most known astrophysical phenomena. Recent radio telescopes like LOFAR and the upcoming Square Kilometre Array are peering deeper into their mysteries, mapping their magnetic fields and hunting for connections to other galactic features. What they've found only deepens the intrigue. Some loops appear to align with known filaments of the Milky Way's magnetic field, suggesting they might be cosmic magnifiers, focusing and amplifying energy from hidden sources. The implications stretch beyond curiosity. If these loops are indeed traces of our galaxy's magnetic skeleton, they could reveal how energy flows through the interstellar medium, shaping star formation and even the distribution of cosmic rays. They might also hold clues to the Milky Way's violent past, chronicling eruptions we've yet to imagine. For now, these silent giants keep their secrets, reminding us that even in our own galactic backyard, the universe still has stories left to tell. Shine a light through the cosmos and something strange happens. Dark streaks appear in the rainbow of starlight, as if the universe itself is hiding barcodes in the sky. These are the diffuse interstellar bands, mysterious absorption lines etched into the spectra of distant stars, and they've been confounding astronomers for over a century. Unlike the predictable fingerprints of known elements like hydrogen or helium, these bands are broad, fuzzy, and stubbornly resistant to identification. They're cosmic graffiti, spray painted across the galaxy by an artist we can't yet name. The puzzle began in the early 1900s when astronomers first noticed these unusual lines while studying starlight filtered through interstellar clouds. At first, they assumed they'd found new elements, perhaps exotic forms of matter waiting to be catalogued. But decades of lab experiments revealed a shocking truth. Whatever creates these bands doesn't match any known substance on Earth. The leading suspect: massive, complex molecules floating between the stars, some with structures so unusual they defy our current chemistry textbooks. Imagine trying to identify a song by hearing just two notes. That's the challenge scientists face. These bands suggest molecules with dozens or even hundreds of atoms, far larger than simple compounds like water or carbon dioxide. Some might resemble polycyclic aromatic hydrocarbons, the sooty remnants of burned-out stars. Others could be carbon chains, cage-like fullerenes, or even organic molecules related to the building blocks of life. But here's the twist. Lab experiments can't yet recreate the exact signatures we see in space, leaving us with a gallery of suspects but no smoking gun. The implications ripple far beyond astronomy. If these bands do trace vast organic molecules, they could be the raw materials for planets and life. Picture interstellar clouds peppered with cosmic Lego bricks, drifting until gravity assembles them into something new. Yet the mystery deepens with each observation. Some bands appear only in certain regions of the galaxy, hinting at environmental factors we don't understand. Others vary in intensity, as if the molecules responsible are shifting forms under different conditions. New tools are finally cracking the case. The James Webb Space Telescope's infrared eyes can probe these bands with unprecedented precision, while advanced quantum chemistry simulations test molecular candidates in virtual labs. One tantalizing clue emerged recently when scientists matched a few bands to charged forms of Buckminster fullerene, a soccer ball-shaped carbon molecule. But for every match, dozens of bands remain unidentified, whispering of chemistry we've yet to discover. Why does this matter? Because these ghostly lines are more than cosmic curiosities. They're a ledger of the universe's hidden chemistry, a record of how complex matter forms in the void. Unlocking their secrets could reveal how the building blocks of planets and life are forged in the darkness between the stars. Every unexplained band is a reminder. Even in the vast emptiness of space, the universe is writing its recipes in a language we're still learning to read. Deep in the cosmic static between stars, astronomers have stumbled upon a signal that shouldn't exist, a faint, mysterious glow of microwaves with no clear source. Dubbed anomalous microwave emission, or AIM, this enigmatic radiation flickers across the galaxy, defying straightforward explanation. Unlike the familiar cosmic microwave background, the afterglow of the Big Bang, this emission arises from something far more localized, something tied to the interstellar medium itself. And the leading suspect, tiny, spinning nanoparticles, smaller than a grain of dust, whirling through space like a cosmic ballet of invisible tops. The story begins with radio telescopes picking up unexpected microwave signals coming from dense interstellar clouds. At first, researchers assumed they were seeing thermal radiation heat emitted by warm dust, but the wavelengths were all wrong. This emission was too bright, too polarized, and it followed a pattern that didn't match any known physical process. The only plausible explanation, something on the smallest scales, nanoparticles, perhaps made of carbon or silicate spinning at dizzying speeds, driven by collisions with atoms or the gentle push of starlight. Here's where it gets even stranger. These hypothetical particles, known as polycyclic aromatic hydrocarbons or PAHs, are thought to be abundant in space, remnants of dying stars. When they absorb ultraviolet light, they don't just heat up, they start to rotate, emitting microwaves as they twirl. Picture a child's top, but 1 quadrillion times smaller, spinning millions of times per second. The math suggests this could produce the exact anomalous signals we detect, but not everyone's convinced. Some scientists argue the emission could come from magnetic nanoparticles, their spins aligning with interstellar magnetic fields and releasing energy as they flip. Others propose even wilder ideas, like exotic quantum effects in ultra-cold dust grains. The debate is far from settled, and every new observation adds another layer of intrigue. What's at stake goes beyond curious microwaves. If spinning nanoparticles are confirmed, they could solve multiple cosmic riddles like the unexplained abundance of certain molecules in space, or even the origins of life's building blocks. These tiny specks might be the universe's smallest engines, driving chemistry in ways we're only starting to grasp. For now, telescopes like the Planck satellite and the upcoming James Webb Space Telescope continue to scan the skies, hunting for clues in the microwave whispers of the interstellar medium. Each flicker of anomalous light could be a breadcrumb leading us closer to understanding how the tiniest things in space shape the grandest mysteries of all. Rising like colossal hourglasses from the heart of our galaxy, two enormous bubbles of scorching plasma stretch halfway across the sky, each one towering 25,000 light-years above and below the Milky Way's disk. These are the Fermi bubbles, first spotted in 2010 by NASA's Fermi Gamma-Ray Space Telescope, and they're anything but ordinary. Glowing with high-energy gamma rays, these structures defy expectations, their sheer scale and violence hinting at a cataclysmic event in our galaxy's past. But what could have unleashed such fury? The answer remains one of the most heated debates in astrophysics. At first glance, the bubbles resemble the aftermath of a supermassive black hole's feast, like our own Sagittarius, a star gorging on surrounding gas and belching out energy in titanic jets. Active galactic nuclei in distant galaxies often produce similar structures, their black holes powering luminous lobes that stretch for millions of light-years. But there's a problem. Sagittarius, a star, is quiet today, a sleeping giant. For it to have created the Fermi bubbles, it would have needed to erupt with unimaginable force sometime in the last few million years. Where's the evidence of that eruption? Alternative theories scramble to fill the gap. Some suggest the bubbles are relics of a starburst period, a frenzy of star formation near the galactic center, where hundreds of supernovae exploded in quick succession, pumping energy into space like a cosmic geyser. Others propose the work of dark matter annihilation, with invisible particles colliding and releasing gamma rays in a slow, smoldering fire. Then there's the wild card. Could these bubbles be the scars of a rogue black hole plowing through the Milky Way's core, stirring up chaos before vanishing into the void? The more we study them, the stranger they become. Recent observations reveal substructures within the bubble's filaments, edges sharper than expected, and even hints of correlated X-ray emissions. It's as if we're seeing not just an explosion, but an ongoing process, a dynamic interaction between the bubbles and the surrounding interstellar medium. Mapping their magnetic fields has only deepened the puzzle, with some regions showing organized patterns while others twist in chaotic vortices. What's at stake isn't just a local mystery. The Fermi bubbles offer a front-row seat to galactic-scale energy transport, a process shaping galaxies across the universe. If they're powered by black hole activity, they could reveal how even dormant giants like Sagittarius, a star, occasionally wake to reshape their surroundings. If starbursts or dark matter are to blame, they'd rewrite our understanding of galactic ecology. Every new observation peels back another layer, showing us that even our own backyard holds eruptions vast enough to dwarf human imagination. For now, these gamma-ray ghosts keep their secrets, reminding us that the Milky Way's calm facade hides a history written in fire. Hidden in the deepest corners of space, where temperatures plunge to just 10 degrees above absolute zero, lie strange cosmic nurseries, dense, dark clumps of molecular gas so cold they defy intuition. These aren't just any clouds, they're the birthplaces of stars, cradles of cosmic creation where gravity weaves chaos into new suns. But here's the puzzle. Some of these clumps refuse to collapse, standing stubbornly still in a universe that's constantly shifting. What's holding them up? At first glance, the physics seems straightforward. When enough gas gathers in one place, gravity should pull it inward, crunching atoms until nuclear fusion ignites and a star is born. Yet observations reveal something unexpected: vast reservoirs of gas that linger for millions of years without collapsing. It's like watching a cliffhanger where the avalanche never falls, suspended in mid-air by some invisible hand. The answer might lie in the delicate balance of forces within these clouds. Turbulence, the chaotic churning of gas stirred by supernova shocks or galactic winds, could act like an internal pressure valve counteracting gravity's pull. Magnetic fields threaded through the gas like invisible threads might also play a role, propping up the cloud's structure as if it were caught in a cosmic spiderweb. Then there's chemistry. Complex molecules like carbon monoxide and water ice coating dust grains, subtly altering how energy moves through the cloud and slowing its collapse. But even these explanations leave gaps. Some clouds are too stable, resisting collapse far longer than models predict. Take the famous Taurus molecular cloud, a star-forming region where pockets of gas sit eerily still, as if time itself has frozen. If gravity alone governed these regions, they should have collapsed into stars eons ago. Instead, they linger, teasing astronomers with their defiance. Cutting-edge simulations are now probing these mysteries, revealing just how finely tuned the interstellar medium really is. Tiny changes in temperature, magnetic field strength, or turbulence can tip a cloud from stillness to star-forming frenzy. It's a cosmic tightrope walk where the slightest nudge could ignite a stellar wildfire or leave the gas floating in perpetual quiet. The stakes are higher than curiosity. These cold clumps are the universe's raw material, the stuff of solar systems and planets. Understanding their stability could rewrite how we trace the life cycle of stars, or even reveal new pathways for planet formation. Every unmoving cloud is a challenge to our theories, a whisper that somewhere in the frigid dark, nature still holds secrets we've yet to uncover. Stretching across light years like invisible threads, the interstellar medium is laced with a force both delicate and powerful: magnetic fields. These aren't the simple bar magnet lines you remember from school experiments. They're chaotic, dynamic, and shape-shifting, weaving through space with enough influence to steer entire galaxies. Yet for all their cosmic importance, mapping these fields is like trying to trace the wind's path through a forest. We know they're there, but their full complexity remains one of the universe's best-kept secrets. Take something as seemingly straightforward as star formation. Gravity pulls gas together, but magnetic fields push back, creating a cosmic tug-of-war. In some clouds, these fields act like scaffolding, propping up vast structures against collapse. In others, they twist into spirals, funneling material into newborn stars like water down a drain. The result, a staggering diversity of stellar nurseries, each sculpted by the invisible hand of magnetism. But here's the catch: we still don't fully understand how these fields originate. Are they remnants of the early universe, amplified over eons, or do they emerge anew from the turbulent churn of interstellar plasma? The challenge of studying them is monumental. Unlike light, magnetic fields can't be captured in a snapshot. Instead, astronomers rely on indirect clues: the way starlight polarizes as it passes through dust grains aligned by magnetic fields, or the faint radio whispers of electrons spiraling along field lines. Cutting-edge tools like the Stratospheric Observatory for Infrared Astronomy, SOFIA, have begun peeling back the layers, revealing fields that are far more tangled than predicted. Some regions show orderly patterns, as if combed into place by cosmic forces. Others resemble a knotted ball of yarn, with fields so twisted they generate pockets of intense energy capable of accelerating particles to near light speeds. Then there's the mystery of amplification. Magnetic fields in the interstellar medium are surprisingly strong, up to 1,000,000 times more intense than those in intergalactic space. How do they grow so powerful? One theory points to the dynamo effect, where swirling motions of conductive gas stretch and twist weak fields, amplifying them like a cosmic generator. Another suggests that supernova explosions act as giant magnetic pumps, injecting energy into the surrounding medium. Yet simulations struggle to replicate the intricate structures we observe, leaving gaps in our understanding. What's at stake goes beyond academic curiosity. These fields are cosmic architects, shaping everything from the orbits of dust grains to the grand spiral arms of galaxies. They shield planets from lethal cosmic rays, guide interstellar chemistry, and may even hold clues to the nature of dark matter. every unanswered question about them is a missing piece in the puzzle of how our universe works, a reminder that even the forces we can't see are writing the story of the cosmos. Scattered between the stars, invisible to the naked eye, lies a mystery as old as astronomy itself: interstellar dust. These tiny grains, no larger than a fraction of a human hair, form a cosmic fog that dims starlight, reddens distant galaxies, and hides entire swaths of the universe from view. Yet despite their pervasive presence, these microscopic particles are anything but simple. Their composition, their origins, even the way they interact with light, each aspect is a puzzle challenging our understanding of the cosmos. Take their bizarre optical properties first. When starlight passes through a dust cloud, it doesn't just get dimmer. It changes color. Shorter wavelengths like blue and ultraviolet light are absorbed or scattered more aggressively than red light, giving rise to a phenomenon called interstellar reddening. It's why the sun appears redder at sunset when viewed through Earth's dusty atmosphere, but on a galactic scale. Yet here's the catch: some dust grains polarize light in ways that defy straightforward explanations, suggesting their shapes and alignments are far more complex than mere spheres tumbling randomly through space. Then there's the question of what these grains are made of. Laboratory studies and telescopic observations hint at a mix of silicates, carbon compounds, and even ice-coated minerals, cosmic soot forged in the fiery deaths of stars. But spectroscopy reveals gaps in our knowledge. Certain absorption features in starlight, known as the 217.5 nanometer bump, correspond to no known material found naturally on Earth. Some theories point to graphite or polycyclic aromatic hydrocarbons, while others propose exotic forms of carbon like tiny diamonds or amorphous organic solids. The truth: we're still piecing together the recipe for this cosmic grime. Perhaps the most tantalizing mystery is how these grains form in the first place. In the harsh environment of space, atoms are too sparse to simply stick together like dust bunnies under a bed. Instead, they may grow on the surfaces of larger grains or assemble in the turbulent winds of aging stars. Some could even originate in supernova explosions, where violent shocks forge new elements and blast them into the void. But observations of young stellar systems show dust grains much larger than expected, raising the possibility that some form through processes we haven't yet imagined. What makes interstellar dust more than a cosmic nuisance is its role as a hidden architect of the universe. These tiny particles act as catalysts, providing surfaces where atoms can meet and molecules can form, including the precursors to water and organic compounds. Without them, the chemistry of life might never have gotten started. They also regulate star formation, their shadows cooling gas clouds just enough for gravity to take hold. Yet for all their importance, we've barely scratched the surface of their secrets. Every unanswered question about them is a missing chapter in the story of how the universe builds worlds, and perhaps life itself. Floating in the depths of space like ethereal jellyfish, vast clouds of hydrogen glow with an eerie ultraviolet light, structures so enormous they dwarf entire galaxies. These are the Lyman-alpha blobs, some of the most enigmatic features in the interstellar medium, and they radiate with a brightness that defies easy explanation. Named for the specific wavelength of light they emit, the Lyman-alpha line produced when hydrogen electrons jump between energy states, these blobs shouldn't be visible at all. Yet there they are, spanning hundreds of thousands of light years, their brilliance challenging everything we know about how energy moves through the cosmos. At the heart of the mystery lies a simple question: what's powering them? Normally, hydrogen glows this intensely only when zapped by fierce ultraviolet radiation, typically from newborn stars or voracious black holes. But many Lyman-alpha blobs float in relative isolation, with no obvious source nearby to energize them. It's like stumbling upon a neon sign glowing in the middle of a desert with no power line in sight. Some theories suggest these blobs might be cosmic catchments, where gas funneled by dark matter's invisible gravity piles up and somehow gets superheated. Others propose they're relicts of ancient galactic collisions, where shock waves from long ago crashes still reverberate through the gas, lighting it up like a fading echo of violence. Then there's the puzzle of their shape. Many blobs aren't just amorphous clouds, they're filamentary, with intricate tendrils and bubbles that suggest turbulent histories. Computer simulations hint that supermassive black holes might be the hidden sculptors, their energy jets carving cavities in the gas while simultaneously ionizing it. But some blobs show no signs of such violent influence, leaving researchers to wonder if entirely new physics, perhaps involving cold flows of intergalactic gas, might be at play. The biggest enigma: some of these blobs appear to be cooling rather than heating, in a phenomenon called Lyman-alpha cooling radiation. Dense pockets of hydrogen shed energy by emitting this distinctive light, effectively acting as cosmic radiators. This process could be key to how galaxies form, as it allows hot gas to condense into stars. Yet the scale of these cooling blobs is mind-bending, far larger than any known galaxy, and often disconnected from visible structures. New telescopes like the James Webb Space Telescope are finally bringing these ghosts into focus, revealing details that could crack the case. Early observations suggest some blobs might be swarming with invisible dwarf galaxies, their collective starlight illuminating the gas like fireflies in a fog. Others show signs of being illuminated by quasars whose light has traveled billions of years to reach us, but for every answer, new questions emerge. Why do some blobs pulse in brightness over time? Why do others appear to rotate as if caught in a cosmic whirlpool? What's clear is that these glowing giants aren't just cosmic oddities, they're windows into how the universe builds its largest structures. They might hold clues to how galaxies gather their gas, how black holes influence their surroundings, and even how the cosmic web distributes matter across the void. Every photon of Lyman-alpha light carries a story, and we're only just beginning to learn how to read it. Out of nowhere, a flash, a blip of radio waves so powerful it outshines entire galaxies for a fraction of a second. Then, just as suddenly as it appeared, it's gone. These are fast radio bursts, or FRB, some of the most explosive and fleeting signals in the universe. First discovered in 2007, these cosmic firecrackers have since been detected streaking across space at mind-bending energies, often from billions of light years away. But here's the twist: while their sources remain hotly debated, one thing is clear: they've got a story to tell about the interstellar medium, and we're only just starting to listen. When an FRB races through the cosmos, it doesn't travel untouched. The signal gets stretched, scattered, and distorted by the electrons and magnetic fields it encounters along the way, like a beam of light passing through a stormy sea. This distortion isn't just noise, it's a fingerprint of the invisible material the burst has traversed. By analyzing how much an FRB's signal disperses, astronomers can map the density of electrons in the interstellar and intergalactic medium it crossed. Think of it as cosmic sonar, using these bursts to probe the universe's hidden plumbing. The real enigma: some FRBs repeat, flashing multiple times from the same patch of sky, while others vanish after a single brilliant pulse. This split personality has led to a zoo of theories about their origins. Magnetars, highly magnetic neutron stars, are prime suspects, with some observed producing FRB-like flares in our own galaxy. But there are outliers, one repeating burst traced back to a spiral galaxy's unremarkable outskirts, far from any obvious stellar fireworks. Another appears to come from a globular cluster, a dense swarm of ancient stars where magnetars shouldn't typically form. Could these be neutron stars colliding, black holes spaghettifying stars, or something even stranger like cosmic strings, hypothetical defects in spacetime itself? Then there's the propagation puzzle. As FRBs travel, their interaction with the interstellar medium can reveal astonishing details. Some bursts show intricate substructure, their signals arriving in multiple peaks separated by microseconds, hinting at encounters with turbulent plasma or dense filaments of gas. Others exhibit Faraday rotation, their radio waves twisted by magnetic fields, offering glimpses into the otherwise invisible forces weaving through space. Perhaps the most tantalizing clue lies in a recent discovery, an FRB that passed through the halo of a distant galaxy before reaching us. The burst's dispersion suggested far fewer electrons than expected, implying galactic halos might be far more diffuse than models predict. If confirmed, this could rewrite our understanding of how galaxies accumulate and lose gas over cosmic time. Every new FRB is a potential Rosetta Stone, carrying encrypted messages about the material it's traversed. With observatories like CHIME and the upcoming Square Kilometre Array scanning the skies, we're on the brink of decoding these signals, not just to find their sources, but to use them as backlighting for the universe's hidden structures. The interstellar medium isn't just a bystander in the FRB mystery. It's an active participant, shaping and being shaped by these bursts in ways we're only beginning to unravel. And with each flash, the cosmos sends another whisper, reminding us that even the briefest signals can illuminate the darkest corners of space. In the grand cosmic ledger of elements, one entry stubbornly refuses to balance lithium. According to our best models of the Big Bang, the universe should contain about 3 times more lithium than we actually observe floating between the stars. This isn't just a minor accounting error. It's a glaring discrepancy that challenges our understanding of nuclear fusion, stellar evolution, and the very fabric of the interstellar medium. Where did all that lithium go? The answer might rewrite the story of how elements spread through the cosmos. Let's rewind to the beginning. In the first 20 minutes after the Big Bang, nuclear reactions forged the universe's first light elements: hydrogen, helium, and trace amounts of lithium. Scientists call this process Big Bang nucleosynthesis, and it's one of the most precisely tested predictions in all of cosmology. Yet when we peer into ancient stars or measure lithium in interstellar gas clouds, the numbers don't add up. It's as if someone erased 2 out of every 3 lithium atoms from existence. So where's the missing lithium hiding? One leading theory points to stars themselves not as factories but as cosmic shredders. When lithium drifts too close to a star's searing outer layers, convection can drag it down into hotter regions where temperatures exceed 2.5 million degrees. At those extremes, lithium nuclei collide with protons and shatter, fusing into helium. Essentially, stars might be incinerating their own lithium supply, converting it into invisible ashes. But there's a problem with this tidy explanation. While some stars do show lithium depletion, others, particularly older, metal-poor stars display higher lithium levels than expected. It's like finding untouched jars of preserves in a kitchen where everything else has been devoured. This paradox suggests that lithium's story isn't just about destruction, it's also about redistribution. Supernova and stellar winds could be spraying lithium back into space, but in uneven ways that leave some regions barren while others inexplicably rich. Then there's the interstellar medium's role. Lithium is notoriously fragile in space, easily broken apart by ultraviolet light or cosmic rays. Some researchers propose that lithium atoms bond with dust grains, forming molecules that shield them from destruction. Others speculate that lithium might collect in cold, dense clouds, hidden from our telescopes like treasure buried in cosmic snowbanks. The stakes here are higher than a single element's inventory. Lithium is a cosmic thermometer. Its abundance helps us gauge the conditions of the early universe. If our predictions are off, it could mean gaps in our knowledge of particle physics or even hints of exotic dark matter interactions. Every unresolved lithium atom is a silent witness to processes we've yet to uncover, a whisper from the interstellar medium that the universe's chemical history is far more complex than we imagined. New observations might finally crack the case. High-resolution spectrographs like those on the Very Large Telescope are hunting for lithium in the atmospheres of ancient stars, while radio telescopes trace its presence in molecular clouds. Each dataset adds another piece to the puzzle, but the full picture remains elusive. For now, the missing lithium stands as a monument to the gaps in our cosmic ledger, proof that even the smallest elements can hold the biggest secrets. Slip between the stars and you'll find yourself immersed in an invisible ocean, not cold and dark but shimmering with electrified gas. This is the warm ionized medium, or WIM, a mysterious phase of the interstellar medium where hydrogen atoms have been stripped of their electrons, leaving behind a glowing plasma that stretches across vast swaths of our galaxy. Unlike the dense, cold clouds where stars are born, the WIM is diffuse and searingly hot, with temperatures hovering around 8,000 degrees Celsius, yet it emits no visible light to betray its presence. So how do we know it's there? The answer lies in the faintest of whispers, the gentle hum of radio waves and the subtle fingerprints it leaves on distant starlight. What makes this phenomenon so puzzling isn't just its existence, it's the sheer scale of it. The WIM isn't confined to isolated pockets. It forms a labyrinthine network of ionized bubbles and filaments, threading through the galaxy like veins in a cosmic leaf. Current estimates suggest it fills up to 20% of the volume between stars, a staggering expanse for something so elusive. But here's the real head-scratcher. If this gas is so hot, why hasn't it simply dissipated into space? The energy required to keep it ionized is colossal, yet no obvious power source is visible. Scientists have pieced together a few tantalizing clues. One leading theory points to the relentless ultraviolet radiation blasting from massive stars, their photons energetic enough to rip electrons from hydrogen atoms light years away. Another suspect is supernova shockwaves, which could heat and ionize gas as they ripple through the interstellar medium. Yet when researchers tally up all known sources of ionizing energy, they still come up short, like trying to heat an entire city with a single candle. This discrepancy suggests hidden players, perhaps rogue stars or even exotic processes involving cosmic rays or magnetic reconnection. Then there's the question of structure. The WIM isn't a uniform fog. It's striated with regions of varying density and ionization that shift over time. Some areas glow faintly in hydrogen-alpha light, revealing tendrils shaped by unseen magnetic fields. Others appear as cavities, gigantic bubbles blown by stellar winds or ancient supernova, their walls lined with ionized gas. Mapping these features is like trying to trace the outline of a cloud with your eyes closed, relying on indirect echoes to reconstruct something invisible. New tools are peeling back the layers of this enigma. Radio telescopes like the low-frequency array LOFAR detect the WIM's faint emissions, while spectrographs dissect the way it scatters light from distant pulsars. Each observation adds a piece to the puzzle, but the full picture remains stubbornly out of focus. Why does the WIM cluster in certain regions while avoiding others? How does it interact with the colder, denser phases of the interstellar medium? And what role does it play in the galaxy's larger ecosystem? Could it be a reservoir for future star formation or a graveyard for expired stellar material? One thing is certain, the warm ionized medium is more than just interstellar filler. It's a dynamic, energetic player in the life cycle of galaxies, a phase of matter that defies simple categorization. Every unanswered question about it reflects a gap in our understanding of how energy flows through the cosmos, how stars live and die, and how the raw stuff of the universe organizes itself across light years. The WIM doesn't just fill space, it shapes it quietly and persistently, one ionized atom at a time. At the heart of our galaxy, buried beneath layers of dust and swirling stars, lies a glow that shouldn't be there, a persistent hum of gamma rays with no obvious source. Dubbed the galactic center excess, this mysterious signal has been puzzling astronomers since it was first detected by NASA, a Fermi gamma ray space telescope over a decade ago. It's not the sharp, pinpoint flashes we'd expect from known objects like pulsars or black holes. Instead, it's a diffuse, almost ghostly light spreading across thousands of light years like a cosmic fog. And the leading explanation, it might be the first tangible evidence of dark matter, the universe's most elusive substance, finally revealing itself. The case for dark matter's involvement starts with the signal's peculiar characteristics. The gamma rays cluster neatly around the galactic center, exactly where simulations predict dark matter should be densest. If dark matter particles are colliding and annihilating each other, as some theories suggest, these collisions could produce gamma rays as a byproduct like sparks flying from an invisible fire. Even more tantalizing, the energy of these gamma rays matches predictions for certain hypothetical dark matter particles, particularly those called weakly interacting massive particles, or WIMP. It's as if the universe left us a breadcrumb trail and it leads straight to the heart of the Milky Way, but not everyone's convinced. Skeptics point to alternative explanations hiding in plain sight. One strong contender, a population of undiscovered millisecond pulsars, ultra-dense, rapidly spinning stellar corpses lurking in the galactic core. These cosmic lighthouses emit gamma rays as they rotate, and if enough of them clustered together, their combined glow might mimic the excess we observe. Supporting this idea, recent observations have spotted faint point sources within the excess, hinting at hidden pulsars too dim to resolve individually. Yet the debate rages on. Are these rogue pulsars the true culprits or just red herrings in a much larger mystery? Then there's the wild card cosmic rays slamming into gas clouds. When high-energy particles collide with interstellar material, they can produce gamma rays as a side effect. The galactic center is a chaotic place packed with gas, turbulence, and violent astrophysical processes. Could this messy environment be generating the excess through sheer pandemonium? Some models suggest yes, but the fine details don't quite align. The gamma ray distribution is smoother than this scenario would predict, leaving gaps in the theory. What's at stake goes beyond academic curiosity. If the excess is dark matter, it would be a landmark discovery, a direct window into physics beyond the standard model. If it's pulsars or cosmic rays, it would force us to rethink how these objects behave in extreme environments. Either way, the galactic center is holding something back, a secret it's reluctant to surrender. New instruments like the upcoming Cherenkov telescope array aim to finally crack the case by peering deeper into the gamma ray haze with unprecedented precision. Until then, this eerie glow remains a cosmic riddle, a siren song beckoning us closer to the truth or deeper into the maze. In October 2017, astronomers spotted something extraordinary streaking through our solar system, an object unlike anything seen before. It was moving too fast to be bound by the sun's gravity, meaning it couldn't have originated here. This was our first confirmed interstellar visitor, and it was behaving in ways that defied explanation. Named Oumuamua, Hawaiian for scout or messenger from afar, this enigmatic traveler became one of the most hotly debated cosmic mysteries of the century. At first glance, Oumuamua appeared to be a simple asteroid or comet, a natural wanderer from another star system, but almost immediately anomalies piled up. Its shape was bizarre, long and needle-like, with estimates suggesting it was up to 10 times longer than it was wide. Nothing in our solar system matches that profile. Then came the real curveball. Oumuamua wasn't just coasting on gravity. As it raced away from the sun, it accelerated slightly, as if pushed by an unseen force. Comets often exhibit similar behavior when their ices vaporize in sunlight, creating a gaseous tail that acts like a natural thruster. Yet Oumuamua showed no visible outgassing, no dusty plume, nothing to explain its sudden speed boost. The scientific community split into factions. One camp argued for natural explanations, proposing that Oumuamua might be a fragment of a larger body, shattered by a cataclysmic event in its home system. Perhaps it was made of exotic hydrogen ice, which could sublimate invisibly in sunlight, providing thrust without a visible tail. Or maybe it was a cosmic dust bunny, an ultra-lightweight aggregate of particles held together by weak forces, its peculiar acceleration caused by solar radiation pressure. Each hypothesis had merit, but none fit every piece of the puzzle perfectly. Then came the more provocative idea: what if Oumuamua wasn't natural at all? Some researchers, including Harvard astrophysicist Avi Loeb, floated the possibility that it could be artificial, a relic of alien technology, like a discarded light sail or a derelict probe. The argument hinged on its unusual reflectivity and acceleration pattern, which bore eerie similarities to human-designed solar sails. Of course, extraordinary claims require extraordinary evidence, and most scientists remained skeptical, urging caution before jumping to extraterrestrial conclusions. But the very fact that the debate reached this level underscored how deeply Oumuamua had rattled our assumptions. The irony: by the time we noticed Oumuamua, it was already speeding away, leaving us with only fleeting glimpses and heaps of unanswered questions. Telescopes scrambled to capture every possible photon, but the data was sparse, like trying to reconstruct a novel from a single torn page. Future interstellar visitors might offer more clarity, especially with advanced instruments like the Vera Rubin Observatory coming online. Until then, Oumuamua remains a cosmic Rorschach test, reflecting back our hopes, our biases, and our hunger to understand the unknown. What makes this mystery so compelling isn't just the object itself, it's what it represents. Oumuamua is proof that our solar system isn't an island. The interstellar medium is teeming with unseen travelers, some of which might hold secrets about how planets form, how materials spread between stars, or even whether we're alone in the universe. Every peculiar detail, its shape, its acceleration, its silence challenges us to think bigger, to question harder, and to prepare for the next scout that might drift into view. Because one thing's certain, Oumuamua won't be the last. The cosmos is full of messengers. The real question is whether we're ready to listen. Stretching across the void like cosmic bridges between worlds, vast tendrils of gas weave through the universe, threads so immense they connect galaxies into a single, sprawling network. This is the cosmic web, the largest structure in existence, and its filaments hold the secrets of how the universe organizes itself on the grandest scales. Far from empty space, these ribbons of hydrogen and helium are dynamic rivers of matter, pulsing with energy and shaping the destiny of everything they touch. Yet for all their grandeur, they remain ghostly, so diffuse that spotting them is like trying to trace the outline of a whisper. The cosmic web's filaments are the scaffolding of the cosmos, tracing the invisible gravitational blueprint laid down by dark matter in the earliest moments of the universe. Imagine pulling apart a ball of cotton candy. The delicate strands that stretch between your fingers mirror how these filaments link galaxy clusters across billions of light years. But unlike candy, these structures are anything but fragile. They channel the raw material for star formation, funneling gas into galaxies like cosmic aqueducts. Without them, the universe would be a scattering of isolated islands, cut off from the resources needed to spark new life. Detecting these filaments has pushed astronomy to its limits. Unlike stars or galaxies, they don't emit their own light. Instead, scientists hunt for their shadows, the subtle absorption lines they imprint on the light of distant quasars, or the faint X-ray glow of million-degree gas trapped within them. Recent breakthroughs, like the discovery of the slingshot filament, a 300 million light-year long thread connecting two superclusters, reveal just how intricate this web really is. Some filaments even glow with the ultraviolet signature of ionized hydrogen, illuminated by the radiation blasting from nearby galaxies, like streetlights reflecting off fog. What makes these filaments so mysterious isn't just their invisibility, it's their defiance of expectations. Simulations predict that filaments should be smooth highways of gas, yet observations show they're clumpy, riddled with knots and voids. Some regions are eerily quiet, while others crackle with turbulence, as if stirred by unseen forces. Magnetic fields might play a role, twisting these tendrils into braids or preventing them from collapsing under gravity. Then there's the puzzle of cooling flows, filaments so dense, their gas should chill and collapse into galaxies far faster than it actually does. Something, perhaps heat from cosmic rays or energy transferred by dark matter, is keeping them aloft like a cosmic suspension system. The implications are staggering. Filaments don't just connect galaxies, they feed them, regulating star formation like cosmic umbilical cords. When galaxies cluster at filament intersections, they grow faster, hungrily devouring the gas flowing in. Others, stranded along sparse threads, starve in isolation. This might explain why some galaxies blaze with newborn stars while others fade into quiet retirement. Even more tantalizing, filaments could be hiding the universe's missing baryons, those elusive atoms we've struggled to account for. If so, they're not just structures, they're reservoirs holding the universe's spare change in their wispy embrace. New telescopes, like the upcoming Extremely Large Telescope, aim to map this hidden network in unprecedented detail, probing its chemistry and dynamics. Every filament holds clues not just to how galaxies form, but to the universe's fate. Will they keep feeding growth forever, or will dark energy tear them apart, leaving galaxies stranded in a dying cosmos? The answers are written in the spaces between the stars, etched into the faintest structures we're only beginning to see. The cosmic web isn't just the universe's skeleton, it's its circulatory system, its nervous system, and perhaps its greatest untold story. The universe loves its rules. Dense galaxies brim with stars, while sparse ones fade into obscurity. But scattered across the cosmos are celestial rebels that defy this logic, ultra-diffuse galaxies. These ghostly islands of stars are so faint, so thinly spread, they barely register against the black velvet of space. Some span the width of the Milky Way, yet contain just 1% of its stars, their light so feeble they're practically invisible against the interstellar medium's glow. How do these wispy structures survive in a universe where gravity favors the dense and mighty? The answer might rewrite what we know about dark matter's grip on the cosmos. Take Dragonfly 44, a spectacular enigma discovered in 2015. Lurking in the Coma cluster, this galaxy emits only a faint shimmer, yet the way its stars move reveals a shocking secret. Their velocities suggest the presence of a colossal dark matter halo, weighing as much as the Milky Way's. That's right, a galaxy with almost no visible substance behaves as if anchored by an invisible titan. It's like finding a feather floating in a hurricane, inexplicably holding its ground. This disconnect challenges everything we thought we knew about how galaxies form. If dark matter can cocoon such delicate structures, might it also sculpt galaxies in ways we've never imagined? Then there's the puzzle of their birth. Some ultra-diffuse galaxies appear primordial relics from the early universe where star formation sputtered out before gaining momentum. Others seem to be galactic refugees, stripped of their gas by violent encounters with larger neighbors. The Virgo cluster hosts several of these failed galaxies, their remaining stars flung into loose, sprawling arrangements. But here's the twist: a few ultra-diffuse galaxies defy even these explanations. They float in near-total isolation, untouched by cosmic collisions, their ethereal forms suggesting alternative origins. Could turbulent gas in the early interstellar medium have birthed them? Or do they represent a rare phase of galactic evolution, one where dark matter's distribution takes on unexpected forms? The most tantalizing clue lies in their resilience. Despite their fragility, many ultra-diffuse galaxies endure for billions of years in hostile environments, cluster interiors teeming with gravitational tides, or voids where gas is too scarce to replenish them. Simulations struggle to replicate this longevity unless dark matter plays an unconventional role. Perhaps their halos are exceptionally fluffy, distributing mass in a way that buffers against disruption. Or maybe their dark matter interacts with itself, creating internal friction that stabilizes them like an invisible skeleton. What makes these galaxies more than cosmic curiosities is their potential as dark matter laboratories. Unlike denser galaxies where stars and gas dominate the dynamics, ultra-diffuse galaxies are so sparse that dark matter's influence shines through unmistakably. Studying them could reveal whether dark matter particles collide, whether they cluster differently than predicted, or even whether our theories of gravity need revision. Telescopes like the upcoming Nancy Grace Roman Space Telescope aim to uncover thousands more of these ghosts, mapping their distribution and probing their secrets. Every faint smudge of an ultra-diffuse galaxy is a whisper from the universe's dark side. They shouldn't exist by conventional rules, and yet they drift through the void, silent witnesses to the mysteries we've yet to solve. In their delicate dance with the interstellar medium, they hold clues to the invisible forces that shape all galaxies, ours included. The cosmos doesn't just build giants, it crafts phantoms, and their stories are just beginning to unfold. The math seems simple. For every star that dies in a spectacular supernova explosion, there should be a glowing, expanding remnant left behind, a cosmic gravestone marking its violent end. Our galaxy is littered with the corpses of massive stars, and based on how often these giants die, astronomers estimate we should see around 3 times as many supernova remnants as we've actually catalogued. So where are they all hiding? This cosmic cold case has researchers scouring the interstellar medium for clues, and the answers might rewrite what we know about stellar deaths and the unseen forces shaping our galaxy. One possible explanation is that we're just not seeing them, not because they're not there, but because the interstellar medium itself is playing tricks on us. Younger remnants like the iconic Crab Nebula glow brightly in X-rays and radio waves, their shock waves lighting up the surrounding gas like a neon sign. But as remnants age, they expand and fade, blending into the background noise of the galaxy. Imagine searching for a dying ember in a foggy field. That's the challenge astronomers face when hunting for older remnants. Some might be lurking in the galaxy's thick disk, obscured by dense dust clouds that block their emissions. Others could have dissipated so thoroughly that their energy has dissolved into the warm ionized medium, leaving no distinct trace behind. Then there's the wild card. Not all supernova leave traditional remnants behind. If a star collapses directly into a black hole without the typical explosive fireworks, a so-called failed supernova, it might vanish without the usual glowing aftermath. Recent observations have caught a handful of stars mysteriously disappearing from sight, hinting that this silent death might be more common than we thought. If true, it could explain why so many stellar deaths seem to leave no memorial. But perhaps the most tantalizing possibility is that the remnants are there, just not where we expected. Supernova near the galactic center, for example, might explode into environments so chaotic that their shockwaves get swallowed by the surrounding turbulence before they can form recognizable structures. Alternatively, remnants could be hiding in plain sight, disguised as other phenomena. Some faint bubble-like features in radio surveys, once dismissed as background noise, might actually be the ghostly echoes of ancient explosions. The stakes here are higher than just solving a cosmic census discrepancy. Supernova remnants are the universe's recycling plants, forging heavy elements and scattering them into space to seed future stars and planets. If we're missing a significant fraction of them, we might be underestimating how quickly these elements spread and misunderstanding the chemical evolution of our galaxy. New telescopes like the Square Kilometre Array could finally lift the veil, probing deeper into the interstellar medium to uncover these hidden relics. Until then, the missing remnants stand as a quiet reminder. Even the most violent events in the cosmos can fade into the background, leaving us to piece together their stories from the faintest of whispers. Oxygen should be everywhere, as the third most abundant element in the universe, forged in stellar furnaces and scattered across space by supernova explosions. It ought to permeate the interstellar medium in predictable quantities. Yet when astronomers tally it up, something doesn't add up. Nearly half of the oxygen expected to be floating between stars is missing, vanishing into cosmic thin air without explanation. This isn't just a minor accounting error. It's a full-blown interstellar heist, and solving it could reveal hidden chapters in the life cycle of galaxies. The case begins with spectroscopy, the art of decoding starlight. When astronomers analyze the absorption lines imprinted on light passing through interstellar clouds, they find clear signatures of oxygen atoms, but not nearly enough to match the universe's known production rate. It's as if someone siphoned off vast reserves of this vital element, stashing it somewhere our telescopes can't see. The prime suspect, dust, tiny grains of silicate and carbon floating in space, could be hoarding oxygen by bonding with it to form compounds like water ice, carbon monoxide, or metal oxides. Think of it like rust forming on iron, except these reactions are happening in the freezing vacuum of space, locking oxygen away in molecular prisons. But here's the twist: even after accounting for dust, the numbers still don't balance. Some oxygen remains stubbornly unaccounted for, suggesting a second hiding place. One leading theory points to the warm ionized medium, that diffuse, electrified gas threading through the galaxy. In this hot plasma, oxygen atoms might be stripped of their electrons, becoming invisible to certain wavelengths of light. Another possibility: the missing oxygen could be trapped in colossal reservoirs of cold molecular gas, so frigid and dense that it emits almost no detectable radiation. Imagine searching for ice by looking only for steam. You'd miss the glaciers entirely. Then there's the wild card: what if oxygen isn't hiding at all but has been transformed? In the harsh environments of interstellar space, ultraviolet radiation and cosmic rays can break apart molecules, scattering atoms or converting them into forms we don't yet recognize. Some researchers speculate that oxygen might exist as tiny, solid clusters, nanoparticles too small to reflect light but large enough to evade detection. Others wonder if it's been incorporated into complex organic molecules, the kind that could seed the building blocks of life. The implications reach far beyond a single element's inventory. Oxygen is a key ingredient in water, in the air we breathe, and in the chemistry that makes rocky planets like Earth possible. If we can't trace its journey through the interstellar medium, we're missing a critical piece of how habitable worlds form. New telescopes like the James Webb Space Telescope are turning their infrared eyes toward these cosmic shadows, probing dust clouds and stellar nurseries for whispers of the missing oxygen. Every photon they capture could be a clue, a breadcrumb leading us closer to understanding how the universe stockpiles its most essential elements. What makes this mystery so compelling isn't just the missing atoms, it's what their absence reveals about our blind spots. The interstellar medium isn't a passive backdrop. It's an active chemical factory, constantly transforming and redistributing matter in ways we're only beginning to glimpse. Every undetected oxygen atom is a reminder that the cosmos still holds secrets, even in its most familiar corners. Streaking through the galaxy at breakneck speeds, enormous clouds of gas defy the gentle drift of the interstellar medium, some racing at hundreds of kilometers per second, fast enough to cross the continental United States in less than 10 seconds. These are high-velocity clouds, and their very existence throws a wrench into our understanding of how galaxies like the Milky Way breathe, grow, and recycle their material. Unlike the slow, swirling dance of most interstellar gas, these turbulent structures barrel through space like cosmic interlopers, their origins shrouded in mystery. Where do they come from? The answer might rewrite the story of our galaxy's past and its future. First detected in the 1960s, these clouds are anything but uniform. Some rain down onto the galactic disk in colossal streams, like the Smith Cloud, a massive hydrogen filament plunging toward the Milky Way with enough gas to birth 2 million suns. Others flee outward as if ejected by some ancient cataclysm. The sheer variety hints at multiple origins, each with its own dramatic backstory. One leading theory suggests they're intergalactic hitchhikers, remnants of smaller galaxies torn apart by the Milky Way's gravity, their gas stripped away and left to wander. Picture a cosmic spiderweb with these clouds dangling like dewdrops from invisible threads of dark matter. Then there's the galactic fountain model, where supernova explosions blast gas high above the galaxy's disk, only for it to cool and come crashing back down in high-velocity torrents. Imagine a geyser erupting in slow motion, its spray freezing into icy droplets that plummet back to the surface. But there's a problem. Not all high-velocity clouds fit this narrative. Some contain surprisingly low levels of heavy elements, suggesting they've never been near a star-forming region at all. These pristine clouds might be relics of the early universe, primordial gas that's only now finding its way into galaxies, a delayed delivery of raw materials from the cosmic dawn. The real enigma lies in their impact. As these clouds collide with the Milky Way's disk, they inject energy, turbulence, and fresh fuel for star formation. Simulations show their impacts can trigger waves of stellar birth, like stones tossed into a still pond. But they might also play a darker role. If a massive enough cloud were to strike our galaxy's disk at the wrong angle, it could warp the entire structure, twisting spiral arms out of alignment. Evidence of past collisions might even be etched into the Milky Way's distorted outer reaches, a fossil record of interstellar violence written in gas and starlight. Observing these clouds is a challenge. Their hydrogen emits faint radio waves, detectable only by sensitive instruments like the Green Bank telescope. But newer technologies are peeling back the layers, revealing intricate substructures, filaments, clumps, and even signs of magnetic fields threading through them. Some clouds glow with the telltale signatures of interactions with the galactic halo's hot gas, their edges eroding like ice cubes in warm water. Others appear unnervingly intact, their coherence defying the chaos of interstellar space. What's at stake goes beyond curiosity. High-velocity clouds are galactic delivery trucks hauling matter across unimaginable distances. They might solve the missing metals problem, explaining why young stars sometimes show unexpected chemical abundances. They could also be the key to understanding how galaxies like ours avoid stagnation, continuously renewing themselves with fresh infalls of gas. Every cloud that streaks through the void carries a story of ancient collisions, of explosions long silent, or of primordial gas finally coming home. The interstellar medium isn't just a passive backdrop. It's a dynamic, ever-changing ecosystem, and these high-speed wanderers are its most unpredictable players. Some cosmic rays don't play by the rules, while most high-energy particles zipping through the galaxy trace back to violent events like supernova or black holes. A strange subset appears to originate from nowhere, or rather, from the quiet depths of the interstellar medium itself. These anomalous cosmic rays carry energies too low to come from distant astrophysical powerhouses, yet too high to be explained by local stellar processes. It's as if the void between stars has its own particle accelerator, quietly churning out these enigmatic particles in ways that defy our models of space physics. The mystery starts with their unique composition. Unlike typical cosmic rays, which are mostly bare protons or alpha particles, these outliers are rich in heavier elements like oxygen, neon, and even trace amounts of iron. But here's the twist: they're not fully ionized. Some still cling to a few of their electrons, a telltale sign they haven't endured the brutal conditions near supernova or pulsars. Instead, they seem to have been gently heated and pushed like leaves caught in a cosmic breeze. The leading theory: They might be born from pickup ions, neutral atoms drifting through the interstellar medium until they're zapped by solar wind or interstellar shocks, stripped of some electrons and sent careening toward us with unexpected energy. But the plot thickens. These rays also exhibit a bizarre overabundance of certain isotopes, particularly helium-3, a rare variant of helium that's notoriously hard to produce in significant quantities. Natural nuclear processes in stars generate only tiny amounts of it, yet here it is, popping up in these cosmic rays at levels that leave researchers scratching their heads. Some speculate the interstellar medium might harbor hidden reservoirs of primordial material, pockets of gas untouched since the Big Bang where these isotopes have survived unaltered. Others propose that peculiar magnetic reconnection events where field lines snap and realign could selectively accelerate these particles, favoring certain elements in ways we don't yet understand. The implications ripple far beyond curiosity. If the interstellar medium truly generates these rays, it means there's a pervasive, low-level particle acceleration mechanism woven into the fabric of space itself, one that doesn't require colossal explosions or extreme environments. This could reshape how we think about energy transport in galaxies, or even how life's building blocks spread across star systems. Every anomalous cosmic ray is a fingerprint of processes we've yet to map, a whisper from the quietest corners of the cosmos that still have stories left to tell. For now, detectors like NASA's Voyager spacecraft, now venturing into interstellar space, and the upcoming Interstellar Mapping and Acceleration probe aim to untangle this enigma by sampling these particles directly. What they find could reveal hidden chapters in the universe's grand narrative, ones written not in the blaze of collapsing stars, but in the subtle, relentless churn of the void. The Milky Way isn't floating alone in the void. It's swaddled in a seething, invisible blanket of gas so hot it glows in X-rays. This is the galactic halo, a vast, diffuse sphere of million-degree plasma stretching hundreds of thousands of light-years beyond the visible disk, and it's one of the most enigmatic features of our cosmic neighborhood. Unlike the cooler clouds of the interstellar medium, this gas isn't making stars or weaving dust. It's a roiling, high-energy frontier, and it holds clues to how galaxies like ours breathe, evolve, and even die. Where does this scorching halo come from? The leading suspect is a galactic-scale recycling program. When massive stars explode as supernova, they blast their guts into space at thousands of kilometers per second, heating the surrounding gas to extreme temperatures. Over eons, this material can buoyantly rise into the halo, like steam from a pot of boiling water. Add to that the relentless energy pouring from the Milky Way's supermassive black hole, which occasionally erupts in outbursts powerful enough to inflate giant bubbles of hot gas like the Fermi bubbles we've already explored. Together, these processes create a self-sustaining cycle. Stars die, gas heats, rises, cools, and eventually rains back down to fuel new generations of stars. But the halo's heat isn't just a byproduct of stellar violence, it's also a cosmic insulator. Simulations suggest this scorching envelope acts as a barrier, regulating how much fresh gas from intergalactic space can trickle into the Milky Way. Too much inflow and the galaxy might drown in unprocessed material, disrupting the delicate balance of star formation. Too little and it could starve, its stellar factories sputtering out. The halo's temperature and density determine whether gas condenses into star-forming clouds or remains forever too hot and diffused to collapse. It's the ultimate galactic thermostat, fine-tuning the Milky Way's growth over billions of years. Yet this picture is far from complete. Observations from X-ray telescopes like Chandra and XMM Newton reveal puzzling gaps in the halo's structure, regions where the gas is unexpectedly clumpy or unevenly distributed. Some areas appear almost hollow, as if vast bubbles have been blown clear by ancient explosions we can't yet trace. Others shimmer with filamentary substructures, suggesting magnetic fields might be braiding the plasma into intricate patterns. Even more confounding, the halo's chemical makeup doesn't quite match predictions. It's richer in heavy elements like oxygen and iron than expected, hinting at a turbulent history of galactic cannibalism, where smaller galaxies were torn apart and their metal-enriched guts dumped into the halo's furnace. The biggest mystery, though, is the halo's energy source. Theoretical models struggle to explain how the gas stays so blisteringly hot over such immense volumes. Supernova and black hole activity inject plenty of energy, but radiative cooling should have siphoned off much of that heat over cosmic time. Some hidden mechanism, perhaps dark matter interactions or unresolved microquasar jets, must be reheating the gas, keeping it from settling into a quieter, cooler state. It's like walking into a room where the fireplace died out long ago, yet the air remains scorching hot. Something invisible is still stoking the flames. Unlocking these secrets isn't just academic. The galactic halo is a living archive, its temperature fluctuations and chemical fingerprints recording every major event in the Milky Way's past collisions, outbursts, epochs of frenzied star formation. By decoding its signals, we might finally understand how galaxies like ours persist for billions of years, or why some run out of gas while others thrive. Every wisp of million-degree plasma is a sentence in a story we're only beginning to read, written in a language of X-rays and magnetic fields. And as new telescopes probe deeper into this invisible inferno, one thing becomes clear: the space between galaxies is anything but empty. It's a dynamic, high-energy battleground where the fate of entire worlds is decided. Between the glowing nebulae and bustling star clusters, the interstellar medium holds a paradox: vast regions that appear eerily empty. These cosmic voids, sometimes spanning hundreds of light years, aren't just gaps in the darkness. They're deserts of near-nothingness where gas density plunges to a fraction of its usual abundance. What's baffling isn't just their existence, it's how they defy the universe's tendency to clump. Gravity should pull matter together, leaving no room for such extreme emptiness. Yet these voids persist, silent and sprawling, as if nature carved them with a knife. Take the local bubble, a cavern of hot, thin gas enveloping our solar system. Stretching over 300 light-years, this cavity was likely sculpted by ancient supernova, their shockwaves blasting away nearby material like a cosmic leaf blower. But not all voids are so easily explained. Some, like the Boötes void in intergalactic space, are so devoid of galaxies they've earned the nickname the Great Nothing. While interstellar voids aren't quite as extreme, their emptiness still challenges our models. Turbulence, magnetic fields, and even radiation pressure from stars all play tug-of-war with gravity, sometimes clearing pockets of space with startling efficiency. The real enigma lies in their longevity. Without constant energy input, these voids should collapse or refill as surrounding gas seeps back in. Yet many endure for millions of years, their edges crisp as if held open by invisible hands. One theory suggests magnetic fields act like cosmic force fields, repelling gas and maintaining the emptiness. Another proposes that dark matter, whose gravity shapes the universe's large-scale structure, might anchor these voids, creating stable low-density zones in its invisible web. Then there's the wild card: could some voids be relics of primordial physics, frozen in bubbles from the universe's explosive birth? Mapping these voids is like tracing the contours of a shadow. Astronomers use the dimming of distant starlight or the absence of radio emissions from neutral hydrogen to chart their boundaries. Recent 3D reconstructions reveal an astonishing truth. The interstellar medium isn't a uniform fog, but a sponge-like labyrinth with voids interwoven like bubbles in foam. Some connect into sprawling tunnels, while others dangle like isolated chambers. Their shapes hint at violent origins, supernova chains, runaway star winds, or even past encounters with rogue black holes. What makes these voids more than cosmic curiosities is their role in galactic ecology. By studying them, we've learned that star formation isn't just about where matter gathers, it's also about where it's missing. Voids act as pressure valves, regulating how energy and turbulence propagate through the interstellar medium. They might even nurture star birth indirectly. When a shockwave from a distant supernova slams into a void's edge, the compressed gas can trigger stellar nurseries along its rim. Yet for all we've pieced together, the sheer scale of some voids still unsettles our theories. If the interstellar medium is a cosmic ocean, these regions are its abyssal trenches, unexpected chasms that remind us how much we have yet to explore. Every empty patch is a question mark, a silent challenge to our assumptions about how space organizes itself. And perhaps that's the most humbling truth of all. In a universe teeming with matter, nothingness might hold the deepest secrets. For decades, astronomers have been staring at a cosmic fingerprint that refuses to be identified, streaks of infrared light glowing from deep space, arranged in patterns that don't match any known molecule. These are the unidentified infrared bands, or UIB, a set of spectral lines so consistent they've been spotted in nebulae, star-forming regions, and even distant galaxies, yet their origin remains one of the interstellar medium's most stubborn secrets. Imagine finding the same graffiti tag in cities across the world, spray painted by an artist who leaves no other trace. That's the level of cosmic intrigue we're dealing with here. The plot thickens when you consider the bands themselves. They cluster around specific wavelengths: 3.3, 6.2, 7.7, and 11.3 micrometers, like a secret code written in thermal radiation. Early theories pointed to polycyclic aromatic hydrocarbons, or PAH, as the culprits. These carbon-rich molecules, shaped like tiny snowflakes or fragments of chicken wire, are abundant in soot and smoke, and their vibrational modes could theoretically produce infrared emissions. But here's the catch: lab experiments struggle to replicate the exact spectral signatures we see in space. It's like matching a suspect's handwriting to a note, only to find their pen strokes are similar, but not identical. Then there's the distribution puzzle. These bands glow brightest in regions bathed by ultraviolet light, like the edges of star-forming clouds where young, massive stars blast their surroundings with radiation. That suggests whatever's emitting them is thriving under harsh conditions, possibly even using the UV energy to power its infrared glow. Some researchers propose these could be grander structures, not just simple molecules, but carbon cages like buckyballs or graphene flakes, their surfaces vibrating in unison to produce the observed patterns. Others wonder if we're seeing the spectral signatures of quantum dots, nanometer-scale fragments whose emissions depend on their exact size and shape. The implications reach far beyond curiosity. These unidentified bands might be the universe's hidden chemists, playing a role in how complex molecules form and evolve in space. They could act as catalysts, helping atoms assemble into the precursors of life's building blocks, or as shields, protecting delicate molecules from destructive radiation. Some even speculate they're linked to the diffuse interstellar bands we see in optical light, perhaps two sides of the same molecular coin. New tools are finally bringing us closer to answers. The James Webb Space Telescope's unmatched infrared sensitivity is mapping these bands with unprecedented precision, while quantum chemists run advanced simulations to test thousands of potential molecular candidates. Recent breakthroughs hint at hybrid structures, PAHs with nitrogen or oxygen atoms wedged into their carbon rings, altering their vibrational signatures just enough to match observations. But for every step forward, new questions emerge. Why do some galaxies show stronger bands than others? How do these molecules survive environments that tear apart other compounds? What makes this mystery so compelling isn't just the unmasked molecules, it's what their persistence tells us about the resilience of matter in the cosmos. These infrared fingerprints are more than spectral quirks. They're evidence of a hidden molecular universe, one that operates by rules we're still deciphering. Every unexplained band is a reminder that the interstellar medium isn't just empty space, it's a chemical laboratory, running experiments on scales and timespans we can barely fathom. And somewhere in that vast experiment, the universe is leaving us clues, waiting for us to piece together their meaning. From ghostly dark matter to rogue interstellar visitors, from glowing Lyman-alpha blobs to the missing atoms hiding in plain sight, these 25 mysteries reveal just how little we truly understand about the space between the stars. The interstellar medium isn't just empty void. It's a dynamic, chaotic frontier where the rules of physics twist in unexpected ways, where matter vanishes and reappears, and where forces we can't even detect sculpt the cosmos on scales both vast and infinitesimal. Every answer we've uncovered has led to deeper questions, and every mystery we've solved has revealed 3 more waiting in the shadows. Consider this: we've mapped the farthest galaxies, yet we can't account for half the ordinary matter in our own cosmic backyard. We've detected particles moving at near light speed, but their origins remain elusive. We've found molecules floating in space that shouldn't exist, and structures so enormous they defy explanation. The interstellar medium is the universe's greatest puzzle box, and we've only just begun to pry it open. But here's what makes this journey so thrilling: these aren't just academic curiosities. The secrets hidden in the interstellar medium shape the fate of galaxies, the birth of stars, and even the ingredients that make life possible. They challenge our understanding of reality itself, whispering hints about dark matter, cosmic evolution, and the fundamental laws that govern existence. So what's next? The adventure is far from over. New telescopes like the James Webb Space Telescope and the upcoming Square Kilometre Array are peeling back layers of the unknown. Citizen scientists are poring over data, uncovering anomalies that might lead to breakthroughs. And somewhere out there, another Oumuamua-like visitor might be racing toward us, carrying new riddles to solve. The universe doesn't owe us answers, it's up to us to seek them. So stay curious, look up at the night sky, and wonder what else is hiding in those dark spaces. Dive into the research, join the conversation, and keep exploring. Because the greatest discoveries aren't just about solving mysteries, they're about realizing how much more there is to discover. The interstellar medium isn't just the space between the stars, it's the next great frontier of human understanding, and the story is just getting started.